Hi, welcome to another lesson at EDU Solutions Institute. Now, in today's lesson, we are continuing on our IB physics journey with the concept of the Stefan-Boltzmann Law. Now, in last week's lesson, we looked on the fundamental of gas behavior. Now, let's take it further as we look at what Stefan-Boltzmann Law has to offer. Now, Stefan-Boltzmann Law has the ability to describe or explain to us the behavior of black body objects. Now, what are black body objects? These are objects that are, as you see, black in nature, but they actually are good absorbers and good emitters of radiation or heat. So therefore, his law in summary tells us that the power that is radiated from these black body objects are proportional to its fourth power of the temperature of that black body. So therefore, we have an equation that says L is equal to E sigma A T to the fourth. Now the L here is the power that's radiated, which we call luminosity. So luminosity is the power that is radiated from black bodies, presented in a unit of Watt, W. Now this E represents a quantity that's called emissivity, which emissivity is basically tells us it's a ratio of how much heat is produced by a body as compared to if it was a black body. So therefore, if the object is not a black body, then it will have an emissivity that's less than 1. Because if the black body will give off 10 watts, then that object of the same size, having that same amount of heat inside of it, will not produce 10 watts, will produce less. So it's a less number over 10, hence we get a number that's less than 1. So the emissivity of black bodies will always be 1. So in some cases, you see the equation, you will not see E. But in some cases where the examples are not full black bodies, then we have to consider the effect that the emissivity has, so we put it in our equation. Sigma represents Stefan-Boltzmann's constant, 5.67 10 to the negative 8 watts per meter square per Kelvin to the fourth. And A represents the surface area of the object that's radiating the heat. And then T is the temperature in Kelvin of the black body or of the object that's radiating the heat, and we raise that to the power of 4. So this is basically the equation that we use to show the link between the power of radiation emitted and the temperature of the black body. So therefore it tells us that the power or the luminosity of objects are solely dependent on its temperature. So if the temperature is high, the power or the luminosity is also high. Temperature is low, and the power or the luminosity will be a low value. Now there's another term that's called the apparent brightness. And the apparent brightness is a better word to say, or another word to say, it's the intensity of what is being felt from a source at a specific distance. So when we have a source producing this power of radiation, what are we feeling further at a distance? So therefore, that apparent brightness or the intensity, B, is the luminosity that the black body or the source is producing divided by 4 pi d squared. The d here represents the distance that you are away from the source. And hence we get apparent brightness to have a unit of watt per meter squared. So again, The apparent brightness gives us an idea of how much intensity we're feeling from the source because we're at a distance. And the reason why it's going to be different is if this, let's use the sun for example. If this is our sun and this is Earth, which is smaller in size, when heat is produced by your sun, right, it's going to spread out in equal proportion throughout the galaxy. Right? What we get due to the distance here would be different than if Earth was here. So if Earth is here, if we're getting 3 rays of sun, when it's further apart because the rays are spreading out, we're possibly getting 1. So therefore the area of this radiation is what we have here, and it's dependent on the distance. Because if it's here, the area now becomes this area, bigger area, because of a shorter distance. Bigger distance, the area that it hits will now be smaller. So therefore, we say it's an apparent brightness. It is the intensity that is being felt at a distance. And therefore, intensity overall can be summarized by the power divided by the area. And this is the power of the source over the area that it is being acting on. Alright? And that's how the principle of Stefan-Boltzmann's law is used in talking about black body objects. So stay tuned as we explore more on our IB Physics syllabus. Bye-bye.